So let's talk about prior distributions in the context of generalized linear models. So it's very common for the prior distribution of our regression coefficients to be normally distributed with some mean and some variance that depends on sigma squared beta j, which is just some term, some parameter that you get to specify, and then a dispersion parameter phi that depends specifically on the response distribution, the data distribution that you're working with. So oftentimes working with data distributions that are members of the exponential dispersion family, which is really just a class of exponential family, a class of exponential, uh, a distribution that's a member of an exponential family that has a very specific form, in which case you can factor out this dispersion parameter. So for a normal distribution, then this dispersion parameter phi is going to equal sigma squared, which is where we commonly see in the context of normal error regression models. And in that case, you might choose the prior distribution for sigma squared for phi to be equal to an inverse gamma or something like that. But usually, but when you are specifying the prior distribution of your regression coefficient beta, you often want to include that dispersion parameter so that your prior distribution is scaled properly. Oftentimes, we don't have a lot of information about the impact of our predictors, about the magnitude or the direction of association. So oftentimes we use what's known as the skeptical prior distribution, and we specify this mu beta j to equal 0, which essentially, as a prior distribution, is kind of skeptical in the sense of saying we're not confident that there's any effect for this particular predictor on the response variable. So a prior with a variance that's independent of phi, so in other words, a prior up here that doesn't depend on this dispersion parameter phi, can also be considered. And as long as your prior variance is large, then really this is probably not going to change your results very much. But it's very common to specify the prior distribution for your regression coefficients as a normal distribution where the variance depends on a dispersion parameter phi. So it's quite common to use independent priors for each of your regression coefficients. We actually assume that they are independent of one another. And that's plausible as long as the columns of your X matrix, your matrix of covariates or explanatory variables, are orthogonal or at least aren't too correlated. If we have a lot of correlation between the predictors or explanatory variables of our X matrix, then a lot of people will say that these independent priors are really not appropriate, since we know that at least in a frequentist context, the estimates of our regression coefficients are going to be correlated. So if you don't feel that independent priors for your regression coefficients are appropriate, you can instead use a multivariate prior for your regression coefficients, once again often conditional on the dispersion parameter phi, where the multivariate normal distribution is normal with a mean of mu beta and a covariance matrix of sigma beta, where this sigma beta is going to depend on this dispersion parameter phi. So perhaps the most well-known way to parameterize sigma beta in the context of Bayesian GLMs is to use really just an extension of the Zellner's G-prior that we discussed when we talked about normal error regression models. So in that case, the sigma beta is going to be equal to c squared times negative h beta hat inverse, where beta hat is usually the maximum likelihood estimator of beta for the frequentist model. In other words, you're actually going to fit a frequentist model to your data before you choose your prior distribution. Sometimes this is known as an empirical based approach, where you use the data to actually get some sensible values for your prior distribution. And H beta is the second derivative matrix of the log likelihood. In other words, this is the Hessian matrix of beta in our GLMs. And we actually can write this in closed form or in a more general context, where negative H of beta is going to equal X transpose HX, where this is sort of abusing notation here because this H is not the same as this H right here. And H is an n by n diagonal matrix with the following elements. And so what you're going to do is you're going to take the derivative of the mean of your distribution with respect to eta I, where these are the natural parameters of the response distribution, and you're going to square those and then multiply by the inverse of the variance of your data distribution. If this sounds complicated, it can be, right? So there's some nice theoretical results that allow us to write these diagonal elements in this way. But the good news is I have provided the values of what HI should be for several common distributions. So for a generalized linear model with weights HI, if we have a normal error model with the identity link, then the weights are going to be sigma to the negative 2 power. So basically this is just the inverse of the variance of our data distribution. If you are using a Poisson response distribution with a log link, then those HIs are going to be lambda I, which is the estimated, which are the mean of each individual response, which, as I mentioned before, we're going to have to estimate using results from a frequentist model. And then for the binomial distribution, because we're also going to talk about that in this chapter, I've actually provided the GLM weights for the logit, the probit, and the complementary log-log model, where for this probit model, I use this notation phi of an argument is the density function of a standard normal distribution. So the good news is that even if you don't feel confident in deriving what these HIs should be theoretically, for several of these common distributions, I provided you the form of HI so that you can use that when specifying your prior distribution. When we set c squared equal to n, this is often known as the unit information prior. And this has to do with this relationship to the Fisher's information matrix in frequentist statistics. And essentially, if you compare the Fisher's information matrix, which attempts to quantify the information provided by a single observation, then setting c squared equal to n will have a prior distribution, or at least a covariance matrix for the prior distribution, that's equivalent to the Fisher's information for a single observation. So this is kind of a special case that people oftentimes will use. For the normal distribution, the prior distribution that we've been talking about is actually equivalent to Zellner's G prior, which is nice because the parameterization for the prior distribution we're using now is consistent with the prior distribution we were using in the previous chapter when we discussed normal error regression models. For all of our other models, these HI, these diagonal elements of our H matrix, are going to depend on estimated parameter values for each observation. So I just wanted to briefly remind you how you would do that in these various cases. So for the Poisson response distribution, when our data distribution is a Poisson distribution, then the estimate of lambda I is going to be the exponential function of xi beta hat, where beta hat is the estimated regression coefficients from our generalized linear model fit in the frequentist or from the frequentist framework multiplied by xi or xi transpose, where this is the vector of coefficients for the ith observation. And the reason that we have to take the exponential function is because if you look back at the form of the log linear Poisson regression model, then you see that the log of lambda I is actually equal to xi transpose beta hat, or xi transpose beta. So to get on the right scale, we have to apply the exponential function. Similarly, if we look at the logit link function, for the binomial case, for the binomial distribution, then we can link the probability of success parameter pi I to the inverse of 1 plus the exponential function of negative xi transpose beta hat, or once again, beta hat is going to be the estimated regression coefficients for a generalized linear model fit in the frequentist context. And of course, you can consider what the HI should be for other distributions, but this tells us how to specify the diagonal elements of our H matrix for the two cases of the Poisson distribution and the binomial distribution, which are the distributions that we're going to be focusing on in this particular chapter.